hope everyone is doing well. Today we're going to summarize a paper titled APQ, a joint search for network architecture, pruning and quantization policy. So before we introduce the main research contribution of the paper, we'll first begin by motivating the research contribution of it. So we know that deep learning has prevailed in many real-world applications like natural language processing, computer vision, robotics, virtual reality, and augmented reality. And in most of the cases, we need to carefully design the network architecture to achieve optimal performance within some given constraints. Meaning that when we want to deploy the deep learning model on a piece of hardware, we need to keep in mind some energy consumption constraints and some latency constraints. So the traditional deployment of deep learning models first begins with the model architecture design, where we begin by deciding, for example, on the number of layers and on the number of neurons in the hidden layers, for example. And then in the next stage, we try to compress the model and prune it, like we decide, for example, to remove the some redundant layers or some redundant neurons, and after that we do some hyperparameter tuning. The traditional approach of deploying deep learning models is inefficient as the number of hyperparameters grows exponentially and it might exceed the acceptable human labor bandwidth. There are some approaches to optimize the separate stages of the pipeline, meaning that there are some approaches to optimize the neural architecture search and to optimize the pruning process and the quantization process separately. However, optimizing the separate stages will lead to suboptimal results, and also the three-step strategy still requires considerable search time and energy consumption. So the research question posed in the paper is that can we really optimize the three stages of the pipeline jointly? So the main contribution of the paper is introducing a framework called APQ, a joint design method to enable end-to-end search of model architecture, pruning and quantization policy with light coast. And the core idea behind APQ is the use of what they called a quantization-aware accuracy predictor, which accelerates the search process. So this predictor takes in a model with a quantization scheme and it returns back the predicted accuracy without having to train the model from scratch and getting its accuracy. So now let's define some terms in order to better understand the main contribution of the paper. So this section will summarize the literature review that they did in the paper. So first, the neural architecture search. The neural architecture search is a technique for automating the design of artificial neural networks. It is used to design networks that can outperform the had-designed architecture, and some former NAS algorithms used an RL agent to determine the cell-wise architecture, and some other works on neural architecture search modeled the problem as a pathfinding problem. The process of pruning is the practice of removing parameters from an existing network, and the goal of this process is to maintain the accuracy of the network while increasing its efficiency. And some examples on pruning are fine-grained pruning and channel-level pruning. And finally, quantization is a process of reducing the precision of the weights in the neural network. So for example, instead of representing the weights as using 32 bits, I represent them using 8 bits. Or in some of the extreme cases, I try to represent them using 1 bit, which are called the binary neural networks. And the quantization is a necessary technique to deploy models on hardware platforms like FPGAs and mobile. So now the multi-stage optimization. One of the possibilities of optimizing the whole pipeline together is to optimize the separate stages and then to combine the optimized separate stages together. Meaning that in the first stage, I optimize the neural architecture search and I put my optimized scheme. In the second stage, I consider pruning, and in the third stage, I consider quantization. However, the multi-stage optimization is not efficient at all, since it needs considerable search time and it leads also to a considerable energy consumption, and it also doesn't lead to the optimal solution, it leads to a suboptimal solution. For example, in the paper, the authors considered combining a proxyless NAS, AMC, and HEQ. It didn't lead to an optimal solution, and it took up to 300 GPU hours to find the optimized architecture. So joint optimization tries to find a balance between the configurations of NAS, pruning, and quantization, and it searches for an optimal solution by optimizing the combined stages together. And that's what they did in the paper. They first, in order to optimize them jointly, they first trained a once for all network that covers a large search space. They then built a quantization aware accuracy predictor, and then they constructed a latency energy lookup table, and they did some resource constraint evolution search. So the figure here shows their joint design structure. They first trained a once for all network, which is considered as a neural architecture search scheme. We will summarize the paper for the once for all network in the upcoming video. And they used this network to get data, to sample data to train the quantization aware accuracy predictor. And to do so, they used the transfer learning, like they first trained the predictor on floating point 32-bit architecture models, and then they fine-tuned it on the quantized architecture models. And then they used the results of the predictor in the evolution research. And here they used the lookup table in order to get the hardware feedback. As we have mentioned, the authors of the paper proposed to build a quantization-aware accuracy predictor, which predicts the accuracy of the mixed precision neural network model based on the architecture configurations and the quantization policy. During search, when I'm searching for the optimal model to deploy on my hardware, I use the predicted accuracy by this quantization-aware accuracy predictor instead of the measured accuracy. And the input to the predictor is the encoding of the network architecture, the pruning strategy, and the quantization policy. The predictor that they used is a simple feed-forward neural network model. They used 3 layers with 400 neurons in each layer. And the biggest challenge that they faced is the data collection to train such a predictor. And in order to collect data, they sampled networks randomly from the once for all architecture, and they first trained the network on a 32-bit floating point model, like they trained it on the architecture that they sampled from the once for all network directly, and then they fine-tuned on some quantized architectures. Their optimization is directly based on the measured latency and energy on the target hardware, and in order to do so, they built a lookup table. They collected the energy consumption measurements and the latency measurements from the BitFusion simulator, and they saved the results in a lookup table. And during the evolution research, they simply queried this table to get the energy measurements and the latency measurements. And in order to do so, they leverage the fact that they can actually approximate the latency or energy of the model by summing up the latency and the energy of each layer. And as I've mentioned, they built a lookup table containing the latency and energy of each layer under different architecture configurations and bit width. And when they get the architecture, they break it down into its separate layers, and they query the table to get the measurements of latency and energy of each layer at negligible cost, and then they simply sum them together. And in order to get the architecture, they adopted the evolution-based architecture search to explore the best resource constraint model. And as we mentioned, the evaluation process of the model was replaced with the quantization-aware accuracy predictor. And the resource constraints can be verified by the latency energy lookup table to avoid the direct interaction with the target hardware. So the experimentation, they conducted several experiments to cover two of the most important constraints for on-device deployment, the latency and energy consumption, and they compared the results with some of the state-of-the-art models. They also compared the BitOps with some of the multi-stage optimized. So this table summarizes some of the results in comparison with some state-of-the-art uh, efficient models. As we can see, their models outperform the state-of-the-art models with either fixed precision or mixed precision. And their model, the second model, can have a 2.2% accuracy boost than the mixed precision of MobileNet v2. So it improved actually from 71.9 until 74.1. And their large model achieved even a higher accuracy. And we can notice that the marginal cost of the cloud compute and the CO2 emission is 2 orders of magnitude smaller. These figures show the result on the BitFusion framework under several latency constraints and energy constraints. And we also notice that the APQ models, the red figure, outperforms all of the other models, whether they are fixed precision or mixed precision. And we also notice an interesting thing, which is that under very limited constraints, the APQ models achieve a very significant uh, and higher results than the usual models. And this is also a comparison with the multi-stage optimization model, that the one that we mentioned earlier when they combined proxyless NAS, AMC, and HEQ. Also, APQ achieves better results, which indicates that the joint optimization of the three stages was also better than the optimization of the separate stages. And this also shows the results that APQ achieved under limited BitOps. It also achieved better results than other models. And we notice the comparison with the single path one shot, like it achieved better accuracy with a 2.2 BitOps savings. Thank you for watching my video. Please leave your feedback in the comments and stay tuned for more paper summaries. Thank you.